I am not going to wear the beard and the hair the entire time because it's a lot. It's so warm. But I'll wear it for the next few moments. Also, it's very distracting. And I don't want to be super distracting. Maybe I'll wear the hat. I don't know. We'll start with the joke. That'll give me an excuse to keep wearing it for a few more moments. Angelina hasn't gotten here yet, so.
Hi everyone. I don't think we've done this one yet. Rainbows don't weigh much. They're actually pretty light.
Alright. Oh, let me take this thing off. Woo. It's so warm. The hat serves as a very functional thing to hold this, though. The reason I'm wearing this is Halloween's tomorrow. My daughter will be a unicorn. My son will be a dragon. So I'm a wizard. So there you go. On theme. Plus, Lord of the Rings is my favorite movie. So, yes, this is Harry Potter gown thing, but you get what you can. All right. So, your all's second test is a week from today. I have made a draft of the exam. The exam is going to be about 25, I think I already told you all, 25 multiple choice questions. There'll be 5 free response, and you will pick 4 out of the 5. So it's kind of a little bit less choice, but also kind of the same. I don't know. It's a little bit less ratio-wise choice. But you're not, each one is one problem. To clarify, they're one-part problems. Now, I've uploaded an updated formula sheet that has all the things. I slightly updated the rubric. So I punted I just moved 1 point from this kind of beginning section to the relevant equations. It gives us a bit more resolution. That's kind of where we want the points actually. Yes, there's value in identifying what you're solving for. Yes, there's value in identifying what the givens are. But the main emphasis is, do you know how to solve the problem? So that's where 60% of the points come from. Do you know how to actually solve it? And so just like an extra point got punted there. Otherwise, everything you need is here. Test 2, again, we're going to do a review on Tuesday. Test 2 is everything I'm highlighting. I mean, it's kind of like the same amount of equations as test 1, so that's kind of nice. Resistors, power, the Kirchhoff's law, the charge in a circuit, or charge in a capacitor is a function of time, and then magnetic field stuff. So, anywho, that's there. What I also want to point out is I did make the review, and the review is posted. So the review is posted, the iQuicker questions are posted, so all the materials for studying are available at this point. I tried to get those done before I actually got the test. Well, I got a draft of the test done first, and then I made the review. So the review has questions in it. It's summaries. It's like the last review we did. That's located in the Files tab, Test 2 review. Boom, there it is, along with the clicker questions, both in order and random. So pick your favorite. Those are all there. Now, I told you all this last time. We're sadly not going to be able to get to AC circuits. I know you're devastated. Now, I did make slides on AC circuits. I spent a bunch of time making some nice slides, only to not be able to use them. But they're here if you do want to look through them, whatever. They exist. It's a whole bunch of things, the normal structure and all that jazz. So we're going to finish up inductors today. It'll only take us like 20-ish minutes, 20, 30 minutes. Then we'll start the lab. Then we'll have our review Tuesday. Then we'll have our test. I'm just kind of walking through the end of the semester here. Our test is next Thursday. Review is on the Tuesday. After that, we're not going to have class because there's Veterans Day. Veterans Day is November the 11th. It's a Tuesday. Kind of odd, but that's how it landed. So we will then have 4 class days after that. We'll have the Thursday, then a full week, and then there's just 1 day on the week of Thanksgiving, that Tuesday. We're going to cover electromagnetic waves during the 3 class days, the 13th, the 18th, and the 20th, and then the 25th will be a review day. That's kind of the rest of the semester. And then we'll have our final, December 2nd, which is a week after that. I know it's a little close to Thanksgiving, but I didn't choose these things. Some people have a final the Monday. Ours is the Tuesday. There it is. But yeah, the whole semester, look at that. You can see the rest of the class in one little calendar month thing. So I'll make those slides for that. One last logistics things to point out to you all. You'll probably appreciate this. So we do have a quiz that's due this Friday or this Saturday. Faraday's Law. It's been open. It's due this Saturday. I was informed there's a typo on the units, I think, for one of the answers. So I need to check into that. But otherwise, I think it's fine. What I want to point out is that there is not going to be a quiz due next Saturday. So normally we have a quiz on like this week's content. But this week's content is really just inductors. And there's not enough to really make a whole quiz on, to be honest. The clicker questions that we're doing in class today is kind of the extent of knowledge you need to know. And in the problem sets, it's only the first 3 questions of the last section are ones you can do with inductors. So all that to say, I'm not going to make a quiz on it. So there's not going to be a quiz due next Saturday, meaning there won't be a quiz that opens tomorrow. The quiz for this week is still there. Don't hear what I'm not saying. There's still a quiz on Faraday's Law. There will not be a quiz on inductors. And there will be just one more quiz after that on electromagnetic waves. Because we'll have 3 days, 3 class periods. So I'll just make one quiz to kind of include all that. So just updating you all on all those things. All right, and then I have a plan to make one more AI assignment that'll get posted sometime after test 2, specifically on guides and how to use AI to make variations on problems for purposes of studying. So say like, man, I know I need to practice this topic. How do I make more practice problems, basically, if your teacher doesn't provide them? AI can do that for you. It's great. And so I'll make something about that, and that'll be out after test 2. All right. Any questions about the test or any of this? That's kind of everything for the rest of the class. The final will be cumulative. The final, you will get a 5x8, just one 5x8 note card. The final will be all multiple choice, so it'll be about 40 multiple choice or so to cover everything. The final, the way the questions will be distributed on the final is basically how much time we spend on each topic. That's kind of been how it's been up to this point. That's how it'll continue to be. So the final will include everything from test 1, everything from test 2, and this electromagnetic waves. But it's not like there's going to be a million questions on electromagnetic waves. There'll be a ratio. We spend a week and a half on it. So it'll get the same number of questions as if we spent a week and a half on anything else. That's the idea. All right. So last thing, y'all, inductors. We started with inductors last time. We didn't finish them, but we got real close. So inductors, what are they? They're solenoids. What do these solenoids do? They resist current. Why do they resist current? Because as the current changes in a circuit, they make a field to oppose that change. We've been talking about that with Faraday's Law. And so the idea here, I didn't really maybe express this super well, so I'm just going to make a real quick slide about this. So the basic idea is, say and we're going to see this at the end of the slides. We're going to connect these things to a circuit, but I just kind of want to unpack this. Say we have some voltage. Let's just, call it 5 volts. It doesn't really matter. And then there's a switch, and then there's some loops. We're going to make 2 loops here. It's important that we have at least 2. And then, we have the ground over here. Whatever. So this is a basic circuit. You got a voltage source, you got some loops, and you got a ground. Why am I mentioning this? What's the current flowing through the circuit right now? 0. You need a high and a low. Now, the second I close this switch, current's going to want to start to flow. We know that. We've done circuits. But here's the problem. Here's the idea with inductors. Once this closes, current's going to flow, and I'm going to redraw this loop so we can see it. This current's going to go counterclockwise. Why? Because that's how my loops, I know it's not super clear here, but I'm going to draw that. We're going to have a counterclockwise current because that's the way my loops form. And if you'll remember, right-hand rule number 2, if we have a counterclockwise current, which way will the field point? Out of the page. So this counterclockwise current is going to make a field out of the page. Why does that matter? There's a second loop on top of that. So there's a second loop on top of that. So the first loop is trying to make a field out of the page. Does the second loop want its field to change? No. So what's the second loop going to do? How do I counteract that? I'm going to make a magnetic field into the page. So this second loop here is going to counteract that. That's the idea of the self-inductance. You have all these loops stacked on top of each other, and as the current changes, it makes a field. As the field changes, all the other loops hate that. and so they fight it. That's why these work the way they do. You have to think of it like a bunch of loops stacked on top. That's what a solenoid is. It's a bunch of loops stacked on top of each other. And this is why they oppose the current. So we spent the time last time talking about that. We derived the expression for the inductance of a solenoid, i.e. how much it does, its ability to oppose this current. Now notice that this inductance does not depend upon the current. That's a really important point here. It only depends upon how many loops you have, the area of your solenoid, and how long your solenoid is. That's how strongly this is going to oppose this. So for example, if we had, back to that original equation, it was negative L di dt. This L goes here. So if my current is changing with some, say, 3 amps per second, I multiply that by this inductance we calculate, and that tells me, we call it like the back voltage, the voltage that's being opposing what's going on here. So, inductors. We're going to see them in circuits in a bit, but that's the idea that we talked about. Solenoids are inductors. We put them in circuits, and they oppose a change in current, and it's super, super useful for us. Here's some examples of them. They're basically a bunch of slinkies, compressed or stretched out or bent or other weird things. That's the idea. We did some math with it. We said, hey, what happens if you change some variables? And that's where we left things off. So I just got a couple more things to teach you all. This won't take very long. This one, I'll straight up tell you, is not going to show up in the test just because I tell you I haven't made a question for it. Don't plan on making a question for it. But it's worth talking about very quickly. It's a very quick derivation. The energy stored in an inductor. Remember, so what I want to connect you all to, capacitors and inductors are they're not similar, but they have similar ideas. A capacitor stores energy in an electric field. An inductor stores energy in a magnetic field. So that's the differences between these. An inductor does stuff with magnetic fields. A capacitor does stuff with electric fields. And you can go to the store and you can buy capacitors. You can go to a store, you can buy inductors. And they have different applications. At the end of this PowerPoint, we'll see how they differ as far as applications are concerned. But just like if you all remember from test 1, there's energy stored in a capacitor. It's 1/2 Q times V. This is something we derived way back when. This is the energy stored in a capacitor. We're going to now derive the energy stored in an inductor. It's going to be a different process, but it's one you all can do. So this first part, we're just going to ignore the rest of this for now, one step at a time. P equals epsilon times I. You might look at that and be like, I've never seen that before. You have if I just write it a different way. PIV. P equals IV. They're the same thing. I is I, and V is the same as epsilon. They're the same. So that's where this is coming from. Epsilon acts like voltage, so just put it where V is. If you prefer, well, I put it in front for the next thing will be. But there you go. There's that. And then all we do is we take, what's the definition of epsilon that I taught you at the beginning of this PowerPoint? It's L di dt. That's the definition that we use from inductance at the end. So we just put that in there. Where epsilon is, we put that. So great, that's the first side. The right side is the definition of energy. So specifically with reference to power, if you all remember from physics 1, power is how much energy you use every second. That's the definition of power. Joules per second. How much energy am I changing from one form to another every second? So if you had a 10-watt light bulb, it is changing every second 10 watts of electrical energy, ideally all into light energy. Not quite, some goes to heat, but that's the idea. All right, so, a derivative and an integral are just opposites of each other. So change it to an integral. So we're just going to now take this. We're going to take power. This is power, and we're going to put it right where power is, and then just do the integral. And this is going to be a really simple one-line problem. So U equals the integral, and we're going to do something that's going to look a little silly, but physicists are fine with it. All right, so I just put that where P was, and then there's a dt, and again, this next step's going to look a little silly, but if we just treat these di's and dt's like variables, I have a dt on the top and I have a dt on the bottom, so I can cancel them. Physicists do that. It's a thing. Now, this does change our limits of integration from time to like maximum current or just some amount of current. But there you go. It turns it into that. And that's a really easy integral. L is a constant. What's the integral of I? If I'm integrating I, can I have I squared over 2. Great, we did it. That's the answer. So L, I squared over 2 from 0 to I naught. I naught is just some random current. There it is. That's the energy stored in an inductor. It's done in like 2 lines. Nice and straightforward. Using equations that we have used before. And then here's it, maybe a little nicer. I use lowercase I here to avoid the funkiness, but it's the same thing. Yay! Again, I'm not going to put this, I don't currently have plans to put it on the test, but it's just another equation. Just wanted to show it to you all that these things store energy, and what's interesting is where is this energy stored? It's in the field. The field is the thing that has the energy, and then we can use that field to do stuff. All right. Now we're going to get to the last little thing, and this will be pretty quick. We're going to start to put these in circuits, and we need to understand what's going to happen when they're in a circuit. But before we do that, let's see if we're cool with the equation. So actually, yeah, let's practice this equation. I'm going to put it right here for you all, 1/2 Li squared. How can I store 4 times as much energy in an inductor? If I use 4 times the current, does that accomplish it? 4 times the number of loops, half the length, double the radius. My hint to you is you need one more equation than I have written here. So here I gave you the energy stored in it. Notice that 3 out of the 4 choices don't actually show up in this equation. So you need to find another equation and plug it in. I believe in you. Now I'm going to enter around and ask you questions, as I do. I'll make the lab. See how it goes. I want to look at it really. I went real fancy with it. The pictures, the look around magnets, the pictures. There's a lot of this. The experience is very easy. The setup, doing it precisely requires you to be careful in ways that you have to know to be careful in. So, you'll see what I mean. I tried to kind of get them to think about all the things they need to think about to get good results. Yes, found the other equation.
I always get sick with color but it's fine. I think it's probably stress. I'm terrible stress. Yeah. I forgot. I forget somewhere in there. Take a break all the time. It's impossible for me to relax.
It's not about the money. I've actually it's my biggest fear.
How well acquainted are you with different I just need a sanity check.
I took a class.
So it's a specific type of equation that has to be in this form above. you end up with a second derivative if you're doing it for product.
Okay.
My homework question was show that when you separate variables for this is a heat equation you get to show that this is not in that form. I'm just thinking because K and B naught are different, they're different constants that we started with. There's no way for you to take a derivative of this, get this, get that. I think that's so. Does that make sense though?
Yes, I definitely agree with that. Like, if you can say that, like when you take this,
How could this be? Yeah.
Yeah.
Something like, yeah. Here, P would be K because we just took the derivative of this. But here, how could it be? Oh my gosh, I'm actually. Now I'm like doubting myself.
So here you're trying to.
Because what if P is K, but the derivative of P is negative B naught? Is that possible? Because here we're that's what I'm saying. Like I'm second guessing myself now.
Where did you just come up with?
No, they started in the. Yeah, this was the beginning. Heat flow with convection. Yeah, K is always in there, but this is a special term that makes it not homogeneous. We're doing a big boy problem. Because it is constant for, I don't know.
This is also a derivative over x?
Yeah. Yeah, the function, the spatial function is P. Because you separate the variable from P of x times some function of time x to h. Yep.
Alright. 10 more seconds. I think y'all are pretty good on this. Oh, yeah. This is looking great. Alright. In 5, 4, 3, 2, 1. Alright. So looking at this equation, it has current and it has inductance. This L is not length. That's the thing I told you all before we got to be careful of. So let's actually put L in terms of the things that are given. So if we go back to our previous slides, we find that L equals mu naught N squared times A over L. So that means that my energy is going to be 1/2 times mu naught times N squared times A over L times I squared. And then we're just going to go through each of these options and see what happens. If I make my current 4 times larger, my current is squared. 4 squared is 16 times the original energy. That's not what we want. If I use 4 times the number of loops, the number of loops is also squared. Just to kind of highlight these where these are showing up in the equation. N squared means I'm also going to get 16 times the energy. Not what I want. If I half the length, length is on the bottom. So if I half the length, that means I'm going to get double the energy. That's not what I want either. If I double the radius, currently we didn't have radius in the equation, but if we just go through what each of these letters represent, A is area. The area of this is pi r squared. So if I double the radius, then I'm going to get 4 times the energy because it's squared and 2 squared is that. One of the great way to study is to actually go through the formula sheet. And when you go through the formula sheet, read these like sentences. It sounds stupid, but do you actually know what these equations represent? What every variable represents and what the equation as a whole represents. So for example, this one, this says Q is a function of T equals Q naught 1 minus T negative T over RC. What this says is that my charge is a function of time equals my some charge, it ends up being the maximum charge, times 1 minus e to the amount of time that's happening over r and c. This is an RC circuit, so this is the charging equation. This is how long it takes. This is how much charge I have in a capacitor as time goes on. How do I know it's an RC circuit? There's an R and a C in it. That's a useful way to identify that. So basically going through these, what is this one? FC, what does that even stand for? Centripetal force. Centripetal force equals mv squared over r. What is centripetal force? Those are the questions you should be asking yourself. If you ever run into a variable and you don't actually know what it is, you should probably learn what it is. It's like trying to speak a language and you can say the words, but you don't actually know what they mean. You're going to have a very hard time communicating anything. So, math is a language. Equations are sentences. All right. Now, these are the last few questions for us. And these, so a reminder to you all, these I-quicker questions are kind of the main ones you want to study as far as inductors are concerned. You can do the 2 or 3 problems in inductors in the problem sets as well, but this is the level for inductors. There's only going to be maybe 3 questions on inductors on the test, not much. So here I have a circuit. The circuit has some voltage source, specifically a battery. It's got an inductor. This is actually how you draw inductors in a circuit. They look like what they are. They look like little solenoids. And you got a resistor. And the question is, when will the inductor resist current the most? And my hint to you all is it's going to resist it the most when it generates the largest back EMF. Back EMF just means a voltage that's opposing it. Back, means backwards, it's opposing it. This equation is the back EMF equation, meaning it's how much voltage the inductor is going to oppose the current with. It's L times di dt. So the question is, when is this the largest? Is it immediately after switch S1 is closed? Is it a long time after switch S1 is closed? Is it immediately after switch S2 is closed, or is it a long time after switch S2 is closed? When will this inductor oppose the current the most? See what y'all come up with. I'm optimistic. That equation is the key.
So it really is a chain.
Yes. Yeah. L is purely, that L is connected from the circuit through it across the room. It's still L.
Yeah.
So we're only looking at how T is. So we'll do this. And then ideally for the AC circuits, we put that all together. It'd be great, but time. And I think we're ahead of other people. And I'm still behind. So I don't know. What do y'all think? It is the biggest change in curve. So when will that occur? So switch S2. So if you close S2, the question is, will current flow at all? Yeah, what's the thing driving the current in the circuit? The battery is going to drive. Remember, we only get a current if there's a high voltage and a low voltage. And so unless I see both sides of that battery, unless I have a wire connected to both sides, nothing's going to happen. An analogy for this is you can go outside and you can grab a power line and you'd be fine if you weren't touching anything else. If you touch anything else, now there's a high voltage and a low voltage, and it will go through you real quick. But they actually do work on power lines with like helicopters, and they don't turn off the power lines. In fact, all the electrical work, they don't turn off power lines. They just put themselves to it so that they have the same voltage as it, and they isolate themselves from everything. Anyways, that rules out S2, so now we got an options A and B. Yeah, I didn't answer a question. I rule itself. So what you guys can open it one. Okay. The main question is when using a trap the trick to that is how much current the switch is. When I connect that switch, what's going to want to you put the light switch, current's going to want to start changing. But in series, we're talking about the road. Think about it it's think of it as a road. It's one lane road. It's jammed out. It doesn't matter. There's way at the front, way at the behind. It's a series circuit. Everything's going to be decreased. Whatever it is, it's going to be the same. It'll be the same everywhere. Slow at some point here, it'll be the same slow. So yeah, that you can regular switch a bunch of current tries to flow. It doesn't like that. But as time goes on, that current will grow. But it's not going to grow. Eventually it's going to reach steady state. What's my key there? So for a long time, and then right at the beginning, it hits the chain when it slows. Normally, the lights turn on. In this case, the lights there's a way. Everything with this. Could be a light bulb, could be a resistor, is anything. It could be a functional thing or it could be like anything. Everything is a resistor. All right. Give you all 5 more seconds. It's looking good. 5, 4, 3, 2, 1. All right. So we got 2 switches. Let's rule out the one that does absolutely nothing. For current to flow, you need a high voltage and a low voltage, and you need to see both. I don't care how high up you are in a mountain. If the ground is flat, nothing's going to happen. When's it going to happen? When things going to happen? When you get near the edge, and there's a high point and a low point, you could fall. So, to that end, if I close switch 2 here, nothing will happen. Why? Because I'm only seeing the high voltage. The high voltage is the same everywhere. So fun fact for you all, when they're working on power lines, which are high voltage, they don't turn off the power lines. The people up in those buckets working on those things, the power lines are quote unquote on. Why does it not matter? They're not touching the ground. They isolate themselves from the ground. So they connect themselves to those power lines. The power lines, they're a high voltage. The power lines are a high voltage. It's fine. It's like being at the top of a mountain or like a plateau. It's fine. It's fine. As long as the only reason it becomes dangerous is if things get to the ground. So when do power lines become dangerous? When they hit the ground and now they have a high voltage and the ground has no voltage, and that's a very big difference. Same with birds. Birds can land on power lines and they're fine. When does it become a problem? When they bridge between 2 points and the current can flow through them from that high to the low. So there you go. Switch 2 does absolutely nothing here. Switch 1, that is going to do something. So let's think about switches. If I go over to the, say the lights in this room are off. Well, here, let's just do that. Just turn them off. I can do that. I have the power, I think. Great. Oh, this is taking longer than I thought. All right, the lights are off. Now, normally, if you hit a light switch, what happens to the lights? Ideally, they immediately turn on. These ones take a little bit. There might be an inductor involved. Normally, when you flip a switch, the current goes from nothing to something rapidly. Inductors don't like that. Inductors do not want a rapid change from nothing to something. So the answer here is, when does this inductor oppose it the most? immediately after it's closed, because that's when there's this like big rapid, there's an attempted change and it fights that. So just like we saw with the lights in this room, that was actually a good example. If there's an inductor involved, they will still turn on eventually. It will just take some time. In fact, here's kind of what the graph looks like. We're going to see it on a later slide. The immediate beginning has the biggest change in current, so it's going to fight it the most. But at some point, the current will kind of plateau. So I'll show you all a graph of this just to... So here it is. It's the same graph I just drew. In the beginning, the change in current is maximum. So if we look over here, that means the voltage across it is maximum. But as time goes on, the current's not going to keep increasing forever. We're not going to get a graph where the current increases forever and ever and ever and ever and we reach infinite current. That's nonsense. What will happen is that current will start to finally reach that kind of steady state. And once it does, what's the slope of a flat line? You got this. 0. Great. So the voltage on my inductor is 0. So in the beginning, the inductor does a lot. As time goes on, it just acts like a wire. That's what inductors do for us. They help kind of oppose this change in the beginning, and then as time goes on, they kind of flatten out. And great, that's it. This is called an RL circuit. Why? Because it has a resistor and an inductor. RL. Fantastic. You all do not need to know the equations for this. The next slide is going to show the equations, but I'm not going to test you on them. I will test you on RC circuits. The equations are very similar. They're just opposite. So there you go. There's the circuit. There's the one for current. Yay. Again, we're not going to use it, but just notice it's an exponential, just like the RC circuit is. All right, now, this question I'm not going to test you on. This has to do with capacitors, but I'm doing this for a reason. I just told you that inductors oppose the current the most in the beginning. My question here is, when do capacitors oppose current the most? Do they oppose it the most in the beginning? Do they oppose it the most at the end? That's basically what I want to see if y'all can figure out. So I'll even give you all a hint. C equals Q over V. So if you all rearrange this, V equals Q over C. So using this equation, you can determine what affects the volt. When does a capacitor oppose it the most? When this V is maximum. When is this V maximum? You're going to have to think about it. And this will be our last clicker question, and we'll do the live after this. There'll be like a nice little summary slide after this, and then we'll do the live. So, okay, so yeah, when do you think it opposes it the most? When does that, when does that happen? Quick time or long? The whole point here is that capacitors do the opposite. So there are two devices that do opposite. It's useful to have one versus the other. You didn't know what you wanted.
The weather? I'm so excited that tomorrow's going to be colder. I'm so excited, especially today, seeing my car.
Oh, yeah.
I grew up without my AC today. Like, it's outside of my car.
Yeah, the breeze was nice. Now. I've seen the sunset on Halloween night, it's like 80 degrees out.
It's just like, but I'm going to be so funny. Because it's not normal. It's like, you're
right, yeah.
Like, they're going to be like,
If anybody hasn't changed their costume last night, just get more. What do you think this before? It's just basically saying when is it? We're around it.
yeah, exactly. And it's even better if you can get one of the three, like XYZ.
Yeah. Oh yeah, I forgot. Is it play around with the magnet.
Oh, yeah, there should be magnets somewhere.
I just wanted to test it out.
Magnetize these things. A little electromagnetic free in there. Strong so yeah, I said this check it out. Okay. Yeah, I won't give you all the. Yeah, no, that's good. All right, I'll close this in 5, 4, 3, 2, 1. All right, so just like before, we don't care about switch B. Doesn't do anything. When does a capacitor oppose it? When it's charged. When does it get fully charged? A long time after switch A is closed. So this is the exact opposite of the inductor. Inductor opposed in the beginning, capacitor opposed at the end. Why is this useful? We have devices that can oppose at different times, and so you can make something called filters. So you can filter out high frequencies and low frequencies. Inductors hate high frequencies. What does a high frequency mean? It means the current's going to be changing rapidly. Inductors don't like rapid changes in current. Capacitors are going to oppose low frequencies. When a large amount of time is given for it to charge, it's going to oppose that. And so you can make these things called high-pass filters. They let in low frequencies. You can make high-pass filters let high frequencies through. Low-pass filters let low frequencies through. Then you get something called a band gap filter, which is in between, or band pass filter, which is you only let certain frequencies through. You may be like, why would I care about this? Your phone has to know which phone call to listen to. Right now, every single one of you is getting every single Wi-Fi wave / radio signal / phone signal. It's passing through your phone. There is no avoiding that. You can't just you either get all the signals or you get none of the signals. How does your phone know which signal to listen to? There's filters in here using inductors and capacitors to help that out. They also, I say that's analog. They might also just do digital. Analog means something like this, where it's like, digital means using transistors. Analog means using raw circuit elements. All right, and the last thing's a summary, and then I'm going to open the lab for y'all. You can go ahead and join it. But yeah, this is the summary of that. I'll go ahead and post these. All right, so for the lab, as has been the trend, the key to being successful in this lab is doing a good job in that designing the experiment phase. If you do not think carefully and answer those questions with actual thought and actual brain cells, you will get to the experiment and you will do things and you will do it wrong because you didn't think about why you were doing the things you were doing. That's the whole point of the beginning, is to get you to think about this. So today's lab, I'm going to go ahead and jump over and open it for y'all. Normally we start at 3, so that's why I set it to open at 3, but, we're 15 minutes early. More than that, actually. The goal of this lab is a very simple goal. It's one goal. We're going to use bar magnets, and these are going to be fairly weak magnets, but they should do the job. They're much stronger than the Earth's magnetic field when you get close. We're going to use bar magnets, and we're going to determine how the distance affects the strength of a bar magnet. We're going to try to determine how it affects it specifically. In the beginning of the report, once you all open it, you'll see what I mean. But it's going to tell you that it's going to depend upon R to the N, or R to the B is what I write. So it's going to be distance dependence, but it's going to be some power. Is it R to the 1? Is it R to the negative 1? Is it R to the 2? R to the negative 2? R to the 3? R to the negative 3? Don't look it up until the end. Don't spoil the surprise. Do the experiment. Now, there is some very, very, very important considerations you need to make in this experiment. This experiment is a very simple experiment. You are going to use BIFOX, but there are some steps that you must consider. You have to be careful in your experimental design, and the whole way I designed this lab report is to help you think through the steps and the things you got to be careful of. So take your time. think about it. Read through the beginning part. Again, I'm not gonna actually pass out any bar magnets until like another 5-10 minutes or so, because I want you all to be working through that first part. And that first part, you're not supposed to be messing with it right now. You're supposed to be just thinking through the design. Think before you do. It's one of the most important rules of thumb of life.
Yeah, fairly good. Just straightly. Mine is all over the place.
Oh yeah, I forgot to put something. Did you turn off the calibrator?
How do you do that?
Switch to raw. Okay. So the reason we're gonna do that is it's no longer gonna account for everything. We will account for everything.
Okay, that's already a lot more.
But yeah, you're just gonna kind of move it around and you gotta find your sensors to begin with.
Even I was not.
Yeah, so what you're gonna do is you want to make sure we put it as close as possible.
Yeah.
So we know the X direction is this way, so we're saying your X gets to maximum and your X gets to maximum down here. So now we're gonna find where the Y is maximum. Actually, and you can just take it over here. Swing it behind it.
I thought this direction.
It is. This is way weaker than mine. Okay. Mine was reading like 3,000. Oh, yours is reading much better. That's a much better magnet.
Well, mine was when it was next to the box.
Oh.
So I think that's what it is.
No.
Oh, no.
Oh, yeah, that's much better.
Mine does it too, actually. It was just it's on this side.
Oh, great.
Yeah.
Oh, so we had the wrong side.
So I guess that's a big way to tell which side it's on.
Yeah.
Yeah, it goes down to like 50.
Yes. So good. You are measuring in the thousands. That's what I wanted to be measuring. That's what I measured in. But yeah, a key element to this is finding where the sensor is in your phone. And
Which iPhone?
as
The newest.
I'm gonna tell people this, and I'm gonna have us go around. We should probably be checking with most of the groups where their sensor is. So as we kind of go around, we're going to be checking where are you measuring the field, how are you measuring it. Is yours in the bottom left? So that's really mine's in the bottom left as well. Oh really?
I think so.
Yeah, I actually have no idea where these.
Going up and up. I have no. Is it a?
You're using the south end, right?
So you should be using the X, just the X.
Yeah.
So not the magnitude. So kind of move it up and down and just
Yeah,
see
so it definitely gets higher.
yeah, so yours is somewhere down here then. I mean, I guess. Mine was like right here.
Yeah,
And the thing is, you got to pinpoint the Z location.
So this one, like it's pretty low and then it shoots up.
Yeah, so yours up. Yeah, because the X is.
Yeah, I say mine's like literally in the
Yeah,
bottom.
well, so you both have iPhones, right?
Mhm.
So this is a very good point.
Mine's in like the very
Oh, that's interesting. I kind of figured it'd be standard.
maybe like which one is yours?
No idea.
At some point they might have just like.
It's pretty old.
Yeah, mine was in the bottom left. I assume they just fit them where they can. Like, I don't think there's any
Yeah.
rhyme or reason to the location.
Oh yeah, even the Z now.